It's easier for me. So what do we have? The statement says if I take any bijective holomorphic map on the B01, of course, then we have already seen that the inverse exists by inverse function theorem, and that is also holomorphic. Okay, so that we already know, and so we are assuming, suppose, so since it's a bijective map, so of course it's going to have a zero somewhere. So if the zero is at A, then what we are saying is that our function looks like nothing but some constant times phi of A, where this constant has unique modulus. And what is phi of A? Phi of A is this function, which I had defined in the last class. Phi of A of Z is Z minus A divided by 1 minus A bar Z. Of course, Z minus A was very natural because it was means we wanted to look at a function which was vanishing at A. And since I wanted to map unit circle to unit circle, sorry, unit disk to unit disk, so therefore I had to, you know, introduce this factor in the denominator to take care of that. Okay, fine. So this is what we would like to prove, and of course it should, kind of remind you that the form of the statement of this particular theorem is looking similar to the one which is in Schwarz lemma. Okay, so you see Schwarz lemma also has something of this sort, that there exists a complex number C with mod C equal to 1 such that f of z is C times, of course there the function is the identity function. Okay, so of course, for example, here in the picture should be clear. For example, if I take a equal to 0, then your phi 0 is nothing but the identity function z, right? You can see that clearly. If I take a equal to 0, then phi of 0 is nothing but the identity function z. Okay, so here of course, so that means Schwarz lemma is telling me that some function f of z is equal to constant times phi of 0, right? That is what the second conclusion of Schwarz lemma coming out to be. Is it clear?
Yes, sir.
Yes. So what we are going to do, we are going to use this Schwarz lemma and get the theorem proved. Okay, so that's why, of course it's famous as like in the name of Schwarz lemma, but this could be an independent statement, of course. But generally, you see that lemmas are those ones which are used to prove some particular theorem. So of course, more than the theorem, here one sees that the Schwarz lemma is more important in that way, because the theorem kind of essentially comes from Schwarz lemma. So that's why that particular lemma has a name. Okay, so let us see how do we want to do that. So of course, here you see I need f equal to some c times phi a, right? That is what I have to show. And I told you somehow I am going to use Schwarz lemma. So Schwarz lemma was telling us that it's going to, so Schwarz lemma was giving us functions which were constant times the identity function. Okay, so therefore what I need to do, I need to undo the effect of phi of a. So suppose, like, assuming that we will have eventually f equal to c times phi of a, so what I want to do, I want to undo this effect of phi of a. And we have seen just the other day that, for example, phi of a composed phi of minus a is the identity function. So if at all I want to undo the effect of, like, when I am having phi of a, that means I am having a 0 at a. But let's say I want to undo that and get a 0 at 0, then what I should do is that I should compose with phi minus a. Okay, so that's what I was trying to, by saying that I want to undo the effect of phi of a, I was meaning that. Okay, so let us take so h is equal to f composed phi minus a. So I'm taking this function, and we will show that h of z is equal to c times z for some c in C with mod C equal to 1. Okay, so hence, if that is the case, then we will get Okay, so H is nothing but C times identity. So if you compose phi of A on both sides, you will get F is equal to C times phi of A. Right? All of you agree to this? Yeah? Is it clear what I'm trying to do? Yes?
Yes, sir.
Clear or not? Yeah. Okay, fine. So therefore now my focus will be on this function H, and I want to clearly, as I have already told you, I want to use Schwarz lemma to prove that H of Z equal to C times Z. So I will start by proving one after another all the required things to finally apply Schwarz lemma. Okay, so let us see now clearly. Here I have been, H is a function which is from B01 to B01. Phi A is also a function from B01 to B01. Phi minus A is also a function from B01 to B01. So as a composition, H maps B01 to B01. That's clear. It's very obvious. Okay. And of course, H belongs to the set of all holomorphic maps because my phi A or phi minus A is holomorphic, F is given to be holomorphic, so H is also holomorphic. Okay, so that's good, and moreover, H of 0. What is H of 0? By definition, this is phi F of phi minus A of 0. Now, what is phi minus A of 0? So let us go back to phi minus A. What is phi minus A? So here phi minus A means I will have minus here, plus here. So here, if you put Z equal to 0, what do you get? You get equal to A, right? Correct? On phi minus A, if you put Z equal to 0, then you get A, right? So
Yes,
there
sir.
this is f of a, and I am told that f of a is equal to 0. So this is equal to 0. So clearly h of 0 is equal to 0, and h is a holomorphic function from b01 to b01, and therefore by Schwarz lemma, what do I get? So by Schwarz lemma, first part, Schwarz lemma, let me also write first part for your convenience. We get mod of h of z is less than or equal to mod of z for all z in B01, and mod of h prime of 0 is less than or equal to 0. Okay. So, of course, we will need to prove that if we get equality in one of these two cases, then we will get h of z is equal to constant times mod z, constant times z. Correct? Yeah? Is it clear?
Yes, sir.
So now let us observe what can we do here. Of course, I need to use f is bijective and all of that. So which we have not used so far anyway. So let us see. Um what I'm going to do is the following. First of all, let us observe what is really this h prime of 0. Okay, so what is this quantity? So h prime of 0, this is of course since h is f composed phi minus a, so I can use chain rule. So this is f prime of phi minus a and 0 into phi minus a prime at 0. So this is f prime at a into 1 minus mod a square, okay, because this is what is phi prime of phi minus a prime of 0. I have calculated last day. Yeah, so this was here phi prime a of 0 is this. So whether you take a or minus a doesn't matter. So you get this one. So this is what I have phi prime of a times 1 minus a prime of 0. So, and this guy is given to be that the absolute value is less than or equal to 1. So therefore what I get, so we get mod of h prime of 0 less than or equal to 0. This implies, or let me just not write this, mod of f prime of a is less than or equal to 1 minus 1. 1 divided by 1 minus mod a square. Fine. Okay, so what I am going to do is that I am going to show that we have equality in case of this inequality. Okay, so if I can show that, then what I will get that mod of h prime of 0 is going to be equal to 1, and therefore we will get our result. Is it clear? Yeah.
Yes.
Okay, fine. So let us see how I can do this. So as I said, we show mod of f prime of a is equal to 1 upon mod a square. Okay, fine. I'm going to do this. Now, of course, as I told you, I have so far not used that my function was a bijective holomorphic function. So what, for that purpose, let us consider the inverse of f. Okay. So for this, let g from b01 to b01 be such that G composed F is identity. Okay, so that is G of F of Z is equal to Z. Now, since F of A is equal to 0, and so since this is this, so what do I get? This implies G of 0 is going to be A. So that is what I have. Okay. Now, again, I have taken this G. Now, again, so you keep it in mind that eventually I'm going to, my aim is to show that F is phi, some constant times phi A. So at this point, you just think of phi A. Now, G is its inverse. So effectively, G is like phi of minus A. Now, if you think of like its inverse, then its inverse is going to be again something called phi of a, right? So if I, so for that purpose, what we are going to consider, we are considering this new function. Okay, so consider t, which is phi of a composed g. So again, uh, up to a scalar, this is the identity function. Like that is what you should keep it in mind, kind of. Okay, of course, I have not proved anything about f or g, but you can understand that this is what we are hoping to get. So I take this new function t, which is phi compose g. Now again, t maps b01 to b01 because it's just composition of these maps, and t is of course holomorphic. Okay, so there is no problem with that. And moreover, why did I, again, as I said, I am trying to compose a function, and so that's going to neutralize the effect of that particular function and bring it to some bring it to the identity function or constant times identity. So what is t of 0? Let us say t of 0 is phi a of g of 0, and g of 0 we just saw it is a, so phi a of a, and phi a is defined so that at a this is equal to 0. So again, t a of t at 0 is also equal to 0. Very good. So that means what? Again, we apply Schwartz lemma. First part, again by Schwartz lemma. First part, we get mod of t of z is less than or equal to mod z for all z in b01, and mod of t prime 0 is less than or equal to 1. Okay, so this is what I get. Okay, nice. Now, now that I have this, again, what I am going to do, I need to somehow, I want to prove this, right? So I need to prove that there is no inequality. I rather have an equality. Okay. So if I assume inequality, then I should, get some kind of a contradiction. So what kind of contradiction can I get? Okay. So let us see this. So I have mod of t prime 0 is equal to 0. And as before, we are going to do the same drill, whatever I have done for f prime, I'm going to do it for g prime also. So let us notice what do I get. So t prime of 0 is less than or equal to mod in absolute value less than or equal to 1. Now what is t prime of 0? Again by chain rule, t prime of 0 is phi a prime of g of 0 into g prime of 0. Okay, so this is what I get, and this one implies therefore what is g of 0? G of 0 is a, and I have g prime of 0. So let us see what is phi a prime of a. Phi a prime of a we have calculated 1 upon exactly the quantity which we wanted to get hold of, exactly that 1 upon, but just reciprocal of that. So this is 1 upon, so g prime of 0 divided by 1 upon mod a square. So this implies what? Mod of g prime of 0 is bigger than or equal to 1 by, sorry, is bigger than or equal to 1 minus mod a square. All of you agree to this? Sorry. Uh, just see.
Less than equal to.
Yeah, less than or equal to. Thank you. This is going to be less than or equal to this. So all of you agree to that? We have got this. Yeah? Yes or no?
Yes, sir.
Now, here comes the more important part. What do I know about G and F? G and F, they are inverse to each other. We know that G composed F, G composed F is identity, right? So therefore, G composed F, if I take its derivative, it's going to give me 1. So in particular, if I take this derivative, evaluate at A, that is also going to give me 1. Now, what is G composed F prime at A? So this is G prime of F of A into F prime at A. So this product should be equal to 1. So that means G prime, what is F of A? F of A is 0, and G prime 0 into F prime A is equal to 1. So this is what I am getting. All of you agree to that?
Yes, sir.
Okay. So now, what did I prove? We have already got mod of G prime of 0 is less than or equal to 1 minus mod A square, and mod of F prime at A is less than or equal to 1 over 1 minus A square. 1 over 1 minus mod A square. So this is what I got. Now you tell me, is it possible to have inequality over here? Strict inequality over here? Can I get that?
Not strict possible.
Right? Strict is not possible, because if it is strict, then when I multiply these two, I'm going to get that. So we can't have strict inequalities above, as otherwise we will get that in absolute value mod of g prime 0, g prime of 0 into f prime of a, in absolute value will be strictly less than 1. Correct? All of you agree to that?
Yes, sir.
No matter what place I get 0, no matter what place I get strict inequality, I will have this. Okay, so that's not clearly possible. So in each of the cases, I must have equality. But anyway, of course, I was more interested in the in the second case. So we get mod of f prime at a is equal to 1 upon 1 minus mod a square, and this implies f is so this is what I had said I will show. So this implies mod of h prime of 0 is equal to 1, and having said that, so because that is exactly, this is it, so mod of h prime of 0 is equal to 1, so h is equal to some constant times z for mod c equal to 1. Is it clear to all of you? Yeah. So of course, as I said, I up to this, whatever I have done up to h prime and all that. So up to this, that was okay, but this I could have done for any function, holomorphic function on b01 to b01. But I also had this added information that my function is invertible also. Okay, so like it was a bijective holomorphic function. So then I considered this inverse, And for that inverse, I also got a bound for at g prime of 0, but that bound was effectively the one which, like when I take the multiplication, the things get cancelled, and effectively it gives me that the inequality that was over here, that must be a that must be an equality. Okay, and therefore what we get is that the moment I get equality here, I get mod of x prime 0 is equal to 1, and therefore I get h of z is equal to c times z. So this is by Schwarz lemma part 2. Okay, so by Schwarz lemma second part. Okay, so this is what completes the proof of the theorem that I had left in the last class. Is it clear to all of you?
Yes.
Okay, so therefore now what do we know? We know all possible biholomorphic function on unit disk. Okay, so we can, anytime we can identify those kind of functions. It's going to be in fact identified by the point where it is vanishing. So since it's a bijective holomorphic function, I know that it's going to vanish somewhere. So if I call that point to be a, I don't have to work too much. All I need to consider is the function phi of a, and I just need to identify one particular scalar which is going to be of unit modulus, so that I can just evaluate at any point and accordingly figure out. Okay, so therefore the functions that we are going to have biholomorphic functions on unit circle, they are not unit disk. They are nothing. They are going to be nothing but some constant times phi of a, where this constant has unique modulus. Okay, so that is what we have seen. So this is one particular.
मैं क्या बोल रही थी, कर लिए क्या डिस्कस मेरे पीछे से हो गए कितने आए हैं?
Silva, you want to say something? I do not even understand why you attend classes. If you want to talk over phone, you don't need to attend classes, right? I don't think in this way, if you speak to somebody else over phone, then you are not attentive in the class, and then you are also disturbing others by unmuting. Okay, anyway, so we have therefore understood or like the kind of biholomorphic functions one could get on the unit disk. Now, these kind of functions that we have encountered over here, they are studied in a more general sense. So the kind of functions that I have studied over here, z minus a divided by a minus a bar times z. So these kind of functions can be studied in a more general context. Okay, and those are called fractional linear transformations. So I am not going to spend too much time on these. These are very simple objects. So I'll just briefly touch upon those things. People also call them Mobius transformations. Okay, so here what I'm going to do, as I said, I'm going to study a particular, means like a typical family of functions which generalizes these phi x. Okay, so or it is of similar form, but you will see that it's of a more general nature. Okay, so a map of the form, so let us call it T of z is az plus b divided by cz plus d, is called the fractional linear transformation. Fractional linear transformation. So it's not linear transformation. Of course, there is some shifting, but it's actually fractional as well. Okay, and further, if AD minus BC is not equal to 0, we call it a Mobius transformation. Mobius Mobius transformation. Okay, so Mobius transformation is something of the form Az plus B divided by Cz plus D, where AD minus BC is equal to 0. So let us go back to phi of A. So phi of A was what? Phi of A was Z minus A and then minus A bar Z times plus 1, right? So AD minus BC is what here? AD minus BC is 1, if I'm not mistaken, 1 minus mod A square, right? That is what I'm getting. The determinant here 1 1 and then minus minus, so I have 1 minus mod A square. That is what I am getting, and of course here I am taking mod A to be less than 1. So therefore all these phi A functions, they are actually Mobius transformations. Okay, so what is a Mobius transformation? It's a very simple function of the form Az plus B by Cz plus D, and with the additional property that AD minus BC is not equal to 0. Okay. So what kind of implications this function could have? This function, like this AD minus BC thing being not equal to 0, can actually tell you that this function is an 1 1 function. Okay, so this additional condition ensures that t is 1 1. Okay, so AD minus BC not equal to 0 ensures t is injective. Okay, so why it is injective? Because I can just check az1 plus b divided by cz1 plus d. If it is, let's say, az2 plus b divided by cz2 plus d, then I can just cross multiply and I will get ac z1 z2 plus bc z2 plus ad z1 plus bd. This is d. BD, and this is equal to again AC Z1 Z2 plus BC Z1 plus D A Z2 plus BD. Okay, so I can cancel BD over here. AC Z1 Z2 I can cancel, and therefore what do I get? If I collect all these Z1, so this is AD minus BC times Z1 is equal to again AD minus BC times Z2, and clearly if AD minus BC is not equal to 0, that will give me Z1 is not equal to Z2. Okay, so of course this one is very natural to consider, and this is what we get. Fine, is it clear? Yeah, so this is a very natural condition.
Z1 equals to
Sorry, yeah, so that implies Z1 equal to Z2. Thank you. So is it clear? Yeah, that under this condition we get this map to be injective, and therefore it's a very natural condition that we have put. Okay, now what we can observe is that this function, of course, it's a holomorphic function whenever the denominator is non-vanishing, because the numerator is anyway holomorphic. So all you need to take care is about the denominator, and the denominator is non-vanishing if your z is not equal to, for example, minus d by c. Okay, so that t is holomorphic on c minus minus d by c. Okay, so at this point there is some problem, and again you can notice that, and it takes, you can actually check this, it takes all complex values except a by c. So except this point, this value, t takes all possible complex values. Okay, so you can just this is effectively a linear equation, so you can just cross multiply, like you can just cross multiply and solve. You will always get a solution unless you just start by taking A by C, okay, because then you will cancel your Z. So except for this particular point, you will have all the points in the range, and of course, since the map is 1 1, it will be taken exactly at 1 point. Okay, and so therefore, what do we get? So T maps C minus D by C to C minus A by C. So that is what we are getting. Okay. Now, of course, here you see it does not look really good that we have a couple of points missing, like 1 point in the domain, 1 point in the range. So what we do is that we are going to actually we can think of this function in a bigger generality, okay, and so we can extend t to a function on C union, let's say that I told you about a point at infinity, C union infinity to C union infinity, okay, and you are going to do the most natural thing that is to be done. Yeah, so how do I do that? So set, so I need to first of all map send somewhere to d minus d minus c. I need to send it to somewhere, so I send this to plus infinity, and I also need to send infinity to somewhere, so infinity is going to go to A by C. Okay, so that's kind of obvious because you see here I have ratio of AZ plus B divided by CZ plus D, and for example in place of Z, if you replace, let's say, natural number n, so an plus b divided by cn plus d, as n tends to infinity, its limit is going to be A by C, right? Yeah.
Yes, sir.
So therefore that's a very natural choice, that at infinity the value is taken to be A by C, and minus d by at minus d by c the value is taken to be infinity. Okay, so this is going to be so this t is then a bijective map from C union infinity to C union infinity. Okay, so of course this t has an inverse. Okay, so so t has or has an inverse. Okay, so this inverse is given by T inverse, which is given by dz minus b divided by minus cz plus a. Okay, so this is what you can check, that this composition of these two map is going to be identity. Otherwise, you can also see it in the following form. For example, the way the map T is given, you can think of that your T is associated to the matrix A, B, C, D, where your AD minus BC is not equal to 0. Right? I can think of it in this way, that the map T can be identified to this matrix A, B, C, D, where AD minus BC is equal to 0. Here? Yeah? And the moment you have this condition AD minus BC is not equal to 0, what does it trigger in your hand?
Matrix is invertible.
The matrix is invertible. Okay, so what is, you know, 2 cross 2 matrix, what is the inverse of this matrix?
B minus B minus C A.
D minus B, then minus
Minus C
A times 1 minus AD minus
C
BC.
minus B C.
Right? 1 upon AD minus BC times this. So that's the inverse. Correct?
Yes,
Yeah.
sir.
Now, okay, for a moment you keep this constant over here. I will take care of this, and T inverse. So you know, if mathematics is beautiful, then if T is corresponding to this matrix AB minus ABCD, then T inverse naturally should, you know, somehow correspond to D minus B minus C A. Okay, and you see that is precisely I got over here, and of course I have an extra scalar multiplied out, but you can see that if whatever, let's say I have a matrix lambda mu gamma delta, so this matrix, let's say, gives rise to a Mobius transformation, then the same uh, Mobius transformation will also be given by, let's say, kappa lambda, kappa mu, kappa gamma, kappa delta, right? These two matrices are going to give you the same Mobius transformation for any kappa not equal to 0, right? All of you agree with that? That if you have a matrix and you take just multiply that matrix by some fixed scalar, all the entries, then you are going to get back the same Mobius transformation, right? There will not be any difference whatsoever, isn't it?
Yes, sir.
Yeah. So therefore, actually, the scalars do not matter. So in fact, I can even let go this guy. It doesn't matter. So that is precisely we can see from here. Okay. So this is how we get it, and so T inverse is given by this matrix. Of course, there was a scalar in front of the matrix inverse of ABCD, but that does not really matter. Okay, fine. Now I'm going to, you know, take some kind of basic examples of Mobius transformation, and those transformations are going to be particularly important in our context. Okay, so let us see some basic examples, or let me write rather fundamental examples. Fundamental examples of Mobius transformation. Okay, so what do I take? So T of Z is equal to Z plus B. So that's one kind of Mobius transformation that we take. So which is translation. Okay, and the next one we can take T of Z is equal to, let's say, A times Z. So this is going to be scalar multiplication. Okay, and of course here I am going to take A not equal to 0. Okay, and okay, so if for example I have A of unit modulus, so A will be e power I theta. So you can also treat this as rotation by theta. Okay, so if A is of modulus 1, then writing A equal to e power I theta, we see T is rotation by theta. Rotation by theta. Okay, by an angle theta. So these are the first two, and the last one is the following one, Tz equal to 1 over Z. This is an inversion. Okay, so these are the fundamental examples of Mobius transformations. And now, why do I call them fundamental examples? Because of the following proposition. So what is the following proposition? So let if T is a Mobius transformation, then T is composition of translation, scalar multiplication, and inversion. Okay, so any Mobius transformation can be decomposed into these intermediate, or these simple Mobius transformations, or the like I said, fundamental Mobius transformations. Okay, so let us see how can I get that. So for example, so I need to prove this. So let Tz is given by Az plus B divided by Cz plus D, of course, with Sc minus Bd, sorry, Ad minus Bc is not equal to 0. So this is given. Okay, so if C is not equal, is C is equal to 0, let's say, then clearly you can see that Tz is what? This is A by dz plus B by d, right? So that's clearly T is, T2 compose T1, where I can write T1 is this one. So where T1 sends Z to, let's say, A by D times Z, and T2 sends Z to Z plus B by D. Right? All of you agree to this?
Yes, sir.
Yeah, first you multiply and then you translate. So therefore I can clearly see that in this particular case my Mobius transformation is just composition of the two fundamental transformations, namely the scalar multiplication followed by translation. Okay, fine. So but our life might not be very so simple like that, so we might also have C not equal to 0. So let C not equal to 0. So if C not equal to 0, then I'm going to start with Z. Eventually I need to end up with AZ plus B by CZ plus D. Okay, so let us see how am I going to achieve that. So for this, what I do, start with Z, give it translation. So this is, I'm sending it to Z plus B, D by C, and then I'm going to invert it because in the denominator I need that. So I give inversion 1 upon Z plus D by C, fine, and this is nothing but C divided by CZ plus D. So the denominator I have got already. Okay, and now what I do is that I give a scalar multiplication. So scalar multiplication. So how do I scale this? So somehow I need to bring in this BC minus AD somehow. So I'm going to scale it by BC minus AD divided by C square. Okay, so I'm going to scale it. Of course, C is not equal to 0 in this case. So this times this. And so therefore, what do I have? So this guy is BC minus, or AD minus BC minus AD, doesn't matter, C into CZ plus D. Okay, so after this, I give it a translation. So I translate it by, so I have BC minus AD divided by C into CZ plus D. I translate this by A plus A by C. Okay, so I translate it by A plus A by C, and therefore, what is this going to be? So let us say C into CZ plus D. I have already BC minus AD, plus I have AC, sorry, A into CZ plus D. Fine. So of course I can see AD getting cancelled, and for example, if I take out clearly a C, you will see this is AZ plus B divided by CZ plus D. So this is AZ plus B divided by CZ plus D. Okay, so therefore what I get is that hence you can write, you can verify later, T is equal to T4 compose T3 compose T2 compose T1. So I have had four operations: first translation, then inversion, then scalar multiplication, and then again translation. Okay, so what were all these operations? So this, the T1 was sending Z to Z plus D by C, T2 was sending Z to 1 over Z, T3 was sending Z to, it was a scalar multiplication, so BC minus AD divided by C squared, that's my T3, and eventually T4 was sending Z to Z plus D by C, so that's my T4. Okay, so this is this is the trail that we see, and we get that T is equal to T4, T3, T2, T1. Okay, so this is what we have. Okay, so you have understood that why we call these translation scalar multiplication or the inversion to be the fundamental Mobius transformations, because any Mobius transformation can be obtained by means of these basic Mobius transformations. Okay, so having said that, so this is
Sir, T for Z to Z plus A by C.
yeah, sorry, thank you. Z to A, Z plus A by C. Very good. Yeah. So thank you for pointing out. So effectively, as we can see that main important thing is that we have been able to construct our Mobius transformation by means of composition of these simple looking basic Mobius transformations. Okay. Now I want to talk about some of the properties of the Mobius transformation, and later we will see that how values at three particular point will determine any Mobius transformation. Okay, and given any three particular point, you will be able to also figure out Mobius transformations having that kind of transformation properties. Okay, so what am I doing? So I am going to do, so next is fixed points of Mobius transformation. Fixed points of Mobius transformation. Okay, so what is that? So a complex number, or let alpha belongs to C union infinity. So infinity could be, alpha could be infinity also. Alpha is said to be a fixed point of a Mobius transformation T if T of alpha is equal to alpha. Okay, so if that happens, then I call alpha to be Mobius transformation. Okay, so of course, if I start by taking the identity Mobius transformation, then every point is a fixed point. Okay, so clearly for Tz equal to Z, Tz equal to Z, uh, what do we get for clearly for Tz equal to Z, we have alpha is a fixed point for all alpha in C union infinity. Okay. Okay, so just give me a second. I was getting an important call. Yeah. Okay, so I have this fixed point for every point is a fixed point for this identity map. Now I am going to take a non-identity one. Okay, so in that case, what we will see. So in this case, what we will see is that if T is non-identity, Mobius transformation, then T can have at most two fixed points. So T can have at most two fixed points. That is for a very simple reason, right? Because I can take, for example, so I have, let's say, A alpha plus B divided by C alpha plus D, and this needs to be equal to alpha, so that implies A alpha plus B equal to C alpha square plus D alpha. So therefore I have C alpha square plus D minus A alpha plus B is equal to, sorry, minus B equal to 0. So alpha satisfies at most a degree 2 equation, right? So you can take like that. So you can get, for example, uh, of course there could be two different solutions, there could be only one solution, uh, means alpha could be a double root, your C could be 0, you could have only one solution. So many possibilities we can have. And here you should also remember that I am going to allow my alpha to be equal to plus infinity also. Okay, so that could also be a possibility anyway. So this could be a possibility. For example, if I just have a translation, so in that case z going to z plus beta, z going to z plus b. So in that case my fixed point is I'm going to treat infinity as the fixed point, because infinity is going to go to infinity. Okay, so these are like there will be several such possibilities. So means if I have to write it down, so alpha satisfies a degree 2 equation if C is not equal to 0. Hence, we have at most two solutions in that case. Okay, so alpha may not be solutions of alpha, so may not be difficult, D may not be different. So of course you can take polynomials in such a way that the polynomial has has a double root, so that could be a possibility. And if C is equal to 0 and let's say A is not equal to D, then what do I have? If C is equal to 0 and A is not equal to D, what do I get? I get alpha equal to, then alpha becomes B by D minus A. So that's your possibility. Okay, so here what you can also have is that you can get that yeah. So here in this particular case, if C is equal to 0, then what is my map? My map is, so my map becomes AZ plus B divided by D, right? So that is A by DZ plus B by D. So then alpha equal to B by, sorry, here I have written something wrong, B by D minus A. So that's my alpha, and also T of infinity is equal to infinity. This you can check just by substituting, okay, because your T by infinity image of infinity should be A by C, C is 0, so therefore T infinity is equal to infinity. So you get two fixed points, and if your C is equal to 0, if C is equal to 0 and A is equal to D, so C is equal to 0, A is equal to D, so then the map becomes what? Then you had A plus Z divided plus B divided by D, and D is equal to Z, so this is Z plus B by D. Okay, so in that case, then infinity is the only fixed point. Okay, so in whatever may be the case, you including infinity also, you are going to get you are going to get only two fixed point. Okay, of course, if C is not equal to 0, so clearly you can see that your infinity goes to somewhere A by C. C is not equal to 0, so that's a non that is some particular complex number. So clearly infinity is not a fixed point in that case. If C is equal to 0, of course infinity is a fixed point. Okay, so depending on whether A is equal to D or not, you will get one more fixed point, else you will have only one fixed point. Anyway, so we see that a Mobius transformation can have only at most two fixed points. So this gives us an important and interesting result. Okay, so what is that? So as a corollary to this, we are going to get that Mobius transformation can be determined by its values at three distinct points. Okay, so this is what I can say. So remember, Mobius transformations are invertible. Okay, so that's a very important key important point that we need over here. So remember that a Mobius transformation can be determined by its values at three distinct points. So there is going to be a unique Mobius transformation once you specify the values at three distinct points. Okay, so that's very obvious, because let A, B, C be three distinct points. So let us say um, T of A equal to alpha, T of B equal to beta, T of C is equal to gamma. So suppose I have this, and then if S is another Mobius transformation such that S of A is equal to alpha, S of B is equal to beta, S of C is equal to gamma. So suppose I have this, then what can you say about, for example, S inverse T? What can you say about S inverse T? S inverse T at A. What can I say about that? S is a Mobius transformation. Its inverse is like it is invertible, we know. So what can I say about S inverse T of A?
A
A itself.
A itself. Similarly, at B, it's going to be B. At C, it's going to be C, right? Is it clear?
Yes, sir.
Yeah. So S inverse, let me write S inverse X is equal to X for all X in ABC. Okay. Now, what did we just notice? That if I start with a Mobius transformation, which is not equal to identity, then how many fixed point can it have at most?
2.
2.
So therefore, what can I say about S inverse T?
Identity function.
Has to be identity Mobius transformation. So S inverse T is equal to identity. So that means S is equal to T. T equal to S, whatever you wish. So we see that the moment some Mobius transformation, like you are saying that okay, at these three distinct points, these values are taken, then there is only one Mobius transformation like that. Okay, so of course the matrix could be coming from different matrices. Like you can, as I told you already, I can multiply by any scalar and get back the same Mobius transformation. But just as a map itself, that map is going to be unique. The moment you determine, like you say that at these 3 points, these are the 3 values which my Mobius transformation takes, then the Mobius transformation is uniquely determined. Okay. Now, what I want to do is the kind of the reverse of this. Okay, in the sense that now I want to understand, is it possible that I assign values at 3 distinct points randomly? Like, of course, I need to make sure that the assignment is 1, 1. Okay. And then, can I determine a Mobius transformation out of it? Okay. So now, let us try to understand the converse question. Okay. So, can we assign values at 3 points such that the map is 1 1, at least 1 1 till that point, and determine a Mobius transformation taking those values at those given points. Okay, so this is what I want to now understand, that I have 3 points and the map, its values at those points are also given. Of course, I need to make sure, since I know that Mobius transformations are going to be 1 1, I would like to ensure that the means whatever assignment I wish, that should be 1 1. Then my question is, can I determine Mobius transformation which is going to take those particular values at those particular points? Okay, so that is what I want to understand. Is it clear, the question? Yeah.
Yes, sir.
So indeed, this is actually true, and I am now going to tell you how we can solve this. Okay, so for example, what I am going to do, I am going to start with 3 distinct points, and I am going to give you a prescription to find Mobius transformation where these 3 points take the value 1, 0, and infinity. Okay, because these are the length, then it will be very easy to determine in such a case. Okay, so let Z1, Z2, Z3 be 3 points, 3 distinct points on C union infinity. Of course, infinity is allowed. We first define a Mobius transformation T which takes the values 1, 0, infinity at Z1, Z2, Z3 respectively. So this is what I want to do first. Okay, so of course I don't have sufficient space here, so let me go to the next page. So set T of Z. So I'm giving you an explicit construction. So this is going to be Z minus Z2 divided by Z minus Z3 divided by Z1 minus Z2 divided Z1 minus Z3. So this one is very natural. I'll tell you why. Why the first of all, I need at Z2 my function should vanish. So naturally I should have Z minus Z2 somehow. Then similarly at Z3 I should have infinity. So that means at Z3 my denominator should vanish. So I put Z minus Z3. That's mine. So naturally I get these two. And now I want also that at Z1 the value should be equal to 1. So therefore I divide by, so at Z1 the value means if I don't, if you just ignore this part, then if you just ignore this part, then you can see that at Z1 the value is Z1 minus Z2 divided by Z1 minus Z3. So I just neutralize that and get this one. So sorry, I'm just getting another call. I have to take this. Just to wait. Okay, so this is the first case. So here, of course, I am assuming all my Z1, Z2, because some of these could be, um, infinite. So here, all my points are in complex numbers. So is the first case clear? And that's a very natural case, right? Is it clear to all of you? Yeah. Okay. Next thing is that Now I will, of course, I need to also take care of those cases where my z1 could be, for example, plus infinity, z2 could be plus infinity, sorry, not plus infinity, z1 could be infinity, z2 could be infinity, z3 could be infinity. So in those cases, you see, naturally, if I just look at this one, okay, so that takes care when z2 and z3 are complex numbers, and even z1 is infinity, this is good enough, right? So if z1 is infinity in this case, because at infinity, of course, this is coming out to be, in this kind of a form, infinity by infinity, of course the coefficient is 1 by 1, so therefore at infinity the value is going to be equal to 1. That was our goal anyway. And now let's say I need to find means 0 at infinity. So how can I get 0 at infinity? So for that, what I do, I consider this point z1 minus z3 divided by z minus z3. Okay, so here if z2 is equal to infinity. Okay, so of course if you put z2 in the denominator at infinity, you are going to get 0, no issues. And similarly, if z3 is equal to infinity, then you are just going to do the same thing, z minus z2 divided by z1 minus z2. Okay. So you just, from, if you look at in this factor, so in the first case, when I have z1 equal to infinity, you just ignore the terms where z1 is appearing. Okay, when z2 is infinity, you are kind of ignoring the points where in ignoring the factors where z2 is appearing. Now if z3 is infinity, you are going to ignore the factors where z3 is appearing. Okay, because they are going to, effectively, since I am working with infinity, nothing is going to, like, those factors are not needed. Is it clear? Yeah. So I'm sure if you remember this one formula, which is applicable for uh, complex numbers z1, z2, z3 not equal to infinity, then in each of the particular cases you will be able to, from the formula itself, you will be able to derive it. As I said, when z1 is equal to infinity, clearly in that formula I cannot write something infinity by infinity, right? So I need to forego them. Those terms where z1 is involved, you just let go those. For z2 equal to infinity, you just let go those terms where z2 is there, and like that you can get the formula. Clear? Is it clear to all of you?
Yes, sir.
Yeah. Okay. So now, in fact, um, here I have given you a prescription to find linear Mobius transformation which are taking values 1, 0, and infinity at prescribed points z1, z2, z3, and whatever we have done so far, if I, kind of sum it up everything, then what I get, if z1, z2, z3 are distinct points in C union infinity, and W1, W2, W3, another set of distinct points of C, then there is one and only one Mobius transformation T such that T of Zi is equal to W1 for I equal to 1, 2, 3. Okay, so of course, if there exists one, there will be only one. This only one part we have already proved, because as a corollary we got that MT can be determined by its values at 3 distinct points. So this only one part is already done. So the uniqueness is already done. We just need to now prove the existence. Okay, so proof unicity follows from the corollary above. So next I have to prove the existence. Okay, so here you remember I'm going to use my knowledge of getting Mobius transformation which takes values 1, 0, infinity. I'm going to use that. Okay, so I now need to prove the existence. So how do I show the existence? For that, let T1, T2 be the Mobius transformation such that I do the following. T1 of Z1 is equal to 1, T1 of Z2 is equal to 0, T1 of Z3 is equal to infinity. I know how does T1 look like because I have already given you a formula for this, right? Clear? This we know how to get. Similarly, I can also do T2 of W1 is 1, T2 of W2 is 0, T2 of W3 is infinity. I can also find this. Do you agree that I can get these kind of two Mobius transformations, right?
Yes, sir.
Yes, sir.
Now, what is my aim? My aim is to get my a Mobius transformation which sends Zi to Wi. So, what should I do? Just imagine, what should I do?
T1 to
Composition.
T2 inverse.
Composition of what?
T2 inverse.
Very good. So, consider T2 inverse. Of course, the moment you know how the form of T1, T2 looks like, you can immediately take the inverse. That is very simple. So, T2 inverse T1 is the desired Mobius transformation as T2 inverse T1 of Z1 is equal to T2 inverse of 1, which is W1. Similarly, at Z2 is going to be W2, and Z3 is going to be W3. Okay. All of you agree to this? Yeah. So it was a very simple idea. We just use this fact that we can always invert Mobius transformations, and therefore we get this thing. Okay, so that given any particular set of points, I can always find out Mobius transformations, which are taking those values. Okay, so I hope this is clear to all of you. Yeah. Okay, fine. So now what I'm going to do, I'm going to state some of the statements which I'm not going to prove. As I said, I don't want to spend too much time with Mobius transformation. So these things, if you are interested, you can look up in the books. You will get it. So some important statements which I wish to tell you. So these are without proof. Okay, so what are the statements? So here, of course, we have seen that Mobius transformations are, bijective maps, mapping C union infinity to C union infinity. So what you can do is that you can imagine C union infinity. Already, I have told you about this thing, stereographic projection. So you can imagine C union infinity as the sphere, right? So there, once you treat this as a sphere, then what one can observe is that Mobius transformation, like, so you are, of course, Mobius transformation is a map on C union infinity, and when you treat that like C union infinity, you have an identification already with the sphere. Then in that sphere, what you can see is that this Mobius transformation has very beautiful property that if you take any circle on the sphere, then a Mobius transformation is going to map that particular circle to another circle. So what one says is that Mobius transformation maps circles on the sphere to circles on S. So if you want to translate it in the language of in terms of points in the complex plane, then what you can say is that Mobius transformation maps circles slash straight lines on C to circles or straight lines on C. Okay, because of course you can imagine if I have a straight line on C. Of course, it's an infinite set, and when you will think of this stereographic projection of this, like if you just try to understand what is the corresponding points of a line on the sphere corresponding to the stereographic projection, then you will see that a straight line is going to be nothing but a circle passing through the North Pole. Okay, so that's going to be like that is what is going to be a state is a straight line, and of course if you think of a circle, that's going to also remain a circle. Okay, so Mobius transformation maps circles to circles, if I just want to say in terms of points on the sphere. But if I want to say in terms of points on the complex plane, what I will say is that Mobius transformation actually translate means makes sense a circle or a straight line to a circle or a straight line. Okay, so in fact something stronger. So what I am saying is that treating C union infinity as a sphere S, we can like one can see that a Mobius transformation sends circles on S to circles on S. Okay, in terms of points on C, this implies that a Mobius transformation sends circles slash straight lines to of C to circles slash straight lines. Okay, so this is what is true. One can prove. In fact, something stronger is true. In fact, we have. So I have a theorem. It means we have a theorem of the following kind, that let C1, C2 be two circles on S. There is a unique, actually, sorry, not unique. I don't think so. There is a unique. Sorry, there is a Mobius transformation, not unique, that takes C1 to C1, sorry, C1 to C2, if we specify 3 points, let's say A, B, C on C1 and beta, gamma, sorry, alpha, beta, gamma on C2, then there is a unique Mobius transformation sending C1 to C2 and A to alpha, B to beta, C to gamma. Okay, so in this case, so if I specify 3 points, that's going to be unique. Okay, so if you have to give, means like I'm saying that circles go to circles, that happens, but in fact something more can be done, that you specify any circle, you will always be able to find Mobius transformation which take that circle to the given circle. And if you even specify 3 points, like we have already seen that part, there is a unique Mobius transformation which does the job. Okay, so this is a very interesting and strong statement. So I'm not going to go much more detail into this, and today I will stop because I'm close to the time. And in the next class we will start with singularities. Okay, so the singularities concepts are quite important and beautiful. So we will have this very important theorem called like Cauchy residue theorem, that you will see that makes our life very easy in terms of doing contour integration over like how do I say piecewise smooth closed curves, and we will also see some of the other statements which are important, and of course for that we also need to understand the theory of LoRa expansion. So all these things will come into the segment of singularities. Okay, so I'll stop here. Tell me if there are any other questions.